Hi folks, welcome back. In this video we're going to concentrate on the oscilloscope and the function generator. One of the things we have to do with the oscilloscope is we have to set it up. So we have to kind of calibrate the probe that comes with it. And in order to do that, they provide us with a little signal output here. They didn't put a little hoop on it that we can connect to. So one of the first things I'm going to do is I'm going to use the soldering iron and the solder sucker to suck the solder out of those two holes, put a little metal hoop on there, a little wire hoop, so we can connect up the probe to it in order to get that calibration done. And then I'm just going to take the function generator, I'm going to hook it up to a different oscilloscope just to check out the bandwidth of it to see how flat it is from the lowest frequencies to the highest frequencies. And then I'll use this to check out the oscilloscope to see how flat it is. This covers from about 1 hertz up to 1 megahertz. The DSO is supposed to go up to about 200 kilohertz. So this should be, if it's flat enough, should be fine for testing out how flat and how responsive the oscilloscope is. And we'll go through all the different little controls on the oscilloscope and on the function generator. So let's begin. All right, we're back. I do have to say I'm really enjoying using this iron. So far it's proven to be an excellent iron. Pro tip here. What I like to do when I'm desoldering a previously soldered hole of some kind like this is I'll add a little bit of solder, fresh solder in. Not only does that heat things up and get things closer to where I need it to unsolder it, but it also adds a little bit of fresh solder and flux, which allows us to melt the solder and get it removed from there a little bit better. Sometimes the solder that they make these boards with is not very high in lead content, or it has no lead in it at all, and sometimes that kind of solder is very difficult to remove. So adding a little normal tin lead solder really makes the process a lot easier. So here we'll just heat up one hole at a time and use the solder sucker to remove that solder. Okay, and that's how you use it. You push it down like this, heat up the solder that needs to be removed, put it over the solder joint and press the button. And you see now both holes are completely cleaned out. So now we can add our little wire loop. Now another pro tip, I save the little bits of wire that I cut off leads because it's just handy for this sort of thing, right? And this here in particular is very stiff wire. This is a lead off an LED. And that tends to be very, very stiff, and it's ideal for this sort of application where you're clipping things to it. So what I'm going to do is I'm going to use these pin pliers that came with the tool kit that I got, and I'm going to roll this over the jaws of it to form them into a nice little hoop like that, which we can now trim up and insert into the board and solder it. And hopefully it'll give us a fairly decent connection point to put the scope lead on for our calibration. Now I'll get some fresh solder here and solder it into place. Trim off any excess on the bottom. Now, hope you can see that little hoop that we made there. That allows us to attach the scope lead on and proceed with the calibration. All right, so we're going to set up for that. I'm also going to, as a part of this process, I'm going to be using the bench power supply that we got as part of the kit. So I'm going to use this to power both the oscilloscope and the function generator. They both run from 9 to 12 volts, so we'll probably run them around 10 or 11 volts, and we'll get them checked out. All right, we'll be right back. Let's just quickly go over the controls on the function generator here. You have here, this one here is the amplitude, this one here is the fine frequency control, and this one here is the coarse frequency control. There are a couple of issues with those, but we'll get over that. This is the power input. Like I say, I think this will run anywhere from about 8 to 12 volts. This selector here, this jumper block, selects the range. So the first one is 1 to 10 hertz, then 10 to 100 hertz, 100 to 30 kilohertz, 3 kilohertz, 3 kilohertz to 65 kilohertz, and 65 kilohertz to 1 megahertz. This jumper block up here selects either sine or square wave, or sine or triangle wave, and the output of the sine or triangle wave is here. This one here is the square wave, which the square wave is not adjustable as far as amplitude is concerned, and it basically almost goes to the rail of the power supply. So if you're running a 10 volt power supply, you're going to get almost a 10 volt square wave. There's another slight issue with the square wave too, and we'll show you that on the oscilloscope. And this here is the ground. There's not much to all of that. And those are the controls we're going to be using to run it through the scope. So I'll set up so you can see the scope, and then we'll run it through its frequencies, especially on the sine wave, because that's what we mostly use this for, just to see if it's flat over a reasonable range, at least the range of the oscilloscope, so we can check the oscilloscope whether it's flat or not. Okay, here we are. We're looking at the scope, and we're showing a signal coming from the function generator. This is the lowest frequency I can produce, and the scope is picking up at about 2 hertz, which is about twice what they claim, but that's okay. I mean, it's not often you're going to need low frequencies like this. Now here are a couple of the issues with this square wave. We're looking at it here, we've got 2 volts per division here. I'm powering the function generator with 10 volts at this point in time, and we count 1, 2, 3, 4, 5. So we're going up to 10 volts on the output. So whatever your supply is what you're going to get on the output of your square wave. You cannot attenuate that without some sort of external circuitry with the function generator. Also, I think the same is true for the sine wave and the triangle wave too. We have this offset from 0. So this line here down at the bottom where the arrow is right now, this is 0 volts, and you see the signal begins at 1 volt. So you have this offset from 0, which is a little problematic. It's not that problematic for AC coupled circuits, but for DC coupled circuits, this might be trouble. For instance, if we're using this as a clock input to a CMOS circuit, this would never be seen as going down to 0 volts. So that's a little bit of a problem. You'd have to mitigate that. I have on here a diode. We can go to the other side of the diode, and we can drop that basically down by half a volt. Just let it acquire the signal again, and there we go. So now we're down a little bit lower. So you'd have to maybe have 2 diodes or 3 diodes in series to get it right down to 0 volts. And then you could put a potentiometer on the output to attenuate it so that you could get down to signals for let's say like TTL, where you don't want to go much above 5 volts. And let's see what other frequencies we can get out of it. Let's proceed here with the square wave for a little while. So it gets us up to about almost 20 hertz, 18.5 hertz in that range. If we go up to the next range, so our minimum in this range is 17 hertz. So it's just like the other range, it's about twice as high as what they were saying. We take the coarse control up to its maximum. So here we are at 20 hertz. And then look now what the fine control does. It does a lot more than even the coarse control. So this is getting up to about 200 hertz, which again is twice what the range says. So let's go up to the next range. We're starting at about 300 hertz here, and we can take it up from there. Let's keep going up. Using the coarse adjustment and the fine adjustment. So we're up to now 4.3 kilohertz. Let's continue on up. Next range starts us off at about 4.5 kilohertz and takes us up to like 90 kilohertz. Definitely still around about 10 volts at the peak and plus 1 volt at the minimum. So we've got 9 volts peak to peak still. Here's the highest range. We've got a little bit of jitters entering in here. It's getting quite jittery. Okay, as we go a little bit higher, it gets a little bit better. It's just at the bottom of that range. It looks like it's a little bit jittery, but let's keep our eye on the amplitude and the shape of the waveform. So we're now up to about 260 kilohertz, 350 kilohertz, and we're beginning to lose signal integrity. So we stop having a square wave, I would say, around about 250 kilohertz. You still got a pretty good square wave. It is flat up to 250 kilohertz with the square wave. So let's say what we could do with the sine wave. Okay, so here we have a sine wave set up at around about the bottom of the audio range, 20 hertz, and we have an amplitude of 1 volt peak to peak. And we're going to move up from here to see how flat it stays over this range, because this is the range we're going to test the oscilloscope over. So we're going to move up from here all the way up to about 200 kilohertz, and then we'll test the scope in that range as well. So let's start moving this up. At 200 hertz, we're still at approximately 1 volt. So at this range, we're starting off at 150 hertz. Let's adjust our scope again. And we'll move it on up. We're still maintaining around a volt or so. So far it's being pretty flat. Now we're up to 4.3 kilohertz. We're still flat. We'll move on up. We're getting a little bit of distortion at the top of the waveform. So we're up to almost 89 kilohertz. We're still at a volt. This is where we had a little jitter with the square wave. We have it here as well with the sine wave. So let's move up from here and see if the jitter goes away. Yeah, the jitter is beginning to reduce somewhat. So we're up over 200 kilohertz now, and we're still maintaining 1 volt. Let's keep going a little bit higher. We're getting a little bit more distortion on the top of the wave. And we still got a bit of jitter. So we're right up at 1.2 megahertz. We're still at 0.93 volts, which is pretty good. I mean, with the jitter in there, I'd say, yeah, we're well within the 3 dB point. So there's no issues here with the bandwidth of this function generator. Now we have a quick look at the triangle waveform. See how it's doing now. It is a higher amplitude, so we'll have to bring that down a little bit. We'll bring that down to about a volt. I think this generator actually produces a triangle waveform and then has some internal filtering to give you a quasi-sinusoidal waveform for the sine wave output. Still around about a volt. So yeah, it's pretty flat over its range. Nothing to complain about there. Down to a couple hundred hertz and it's still flat. Okay, so let's now use this to check out the oscilloscope. So I think we're going to end part 1 at this point and continue on with the oscilloscope in part 2. So thanks for watching, and we'll see you then.